Okay, hi guys. So we'll be continuing on seeing more on useful work done and Gibbs energy. So let's get started. So we can write, or actually we know that delta G system at a temperature pressure is equals to non-PV work done. Let's add minus sign on both the sides. So we can write that from here we can write that work done, or rather useful work done, by the system, this would be work done by the system, would be equals to decrease in Gibbs free energy of the system. Okay, so we can also see that if delta G system at a temperature and pressure is equals to 0, then the system is unable to deliver useful work. Okay, now let's see some of the results. So from first law of thermodynamics, we can write that we are considering here only PV work. So we can write that du would be equals to dq plus d of WPV. Okay, and for a reversible process we can write that du would be equals to TdS minus PdV. Let's mark it equation number 1. So this is for reversible process. Okay, and we also know that H is equals to U plus PV. So from here we can write dH would be equals to du plus dPV, or we can write dH would be equals to du plus PdV plus VdP plus dPdV. So as dP and dV both are negligible terms, so dP dot dV would be more negligible, hence we are considering this product as 0 itself. Okay, so we can write that dH would be equals to du plus PdV plus VdP from here. So this is our second equation. Okay, we also know that G, or Gibbs free energy, is equals to H minus Ts. We can also write dG would be equals to dH minus d of Ts. So dG would be equals to dH minus S dt minus TdS minus TD or dt ds. So this term would again be very small, so we are considering this product as 0. So from here we can write dG would be equals to dH minus TdS minus S dt. Okay, so from the second reaction we can write that dH minus this is actually, so we can write this term as TDS. Why? Because du plus pdv would be equals to q, and for a reversible process q would be equals to TDS. So this would be dH equals to TDS plus VdP. So dH minus TDS would be equals to VdP. So dG can be written as VdP minus SdT. Okay. So this would be the third equation. Okay. So now if we look at a condition that what happens in a state of constant temperature. So in constant temperature we can write that dt is equals to 0. Therefore dg would be equals to VdP from here, or we can write that del g upon del p at constant pressure is equals to V. Del g upon del p at constant temperature is equals to V. Okay. And for a particular substance, we can write, let's say for condensed phase, integration of dg would be equals to integral of VdP. So we can write delta g would be equals to V delta P. Okay. And for an ideal gas we can write that we know that dg is equals to VdP, putting the value of V here, which would be nRT upon P dP. So we can write that delta G would be equals to nRT ln P2 upon P1. This can be further written as delta G would be equals to minus nRT ln P1 upon P2, and this could be written as minus nRT ln V2 upon V1. So this is nothing but the work done of a reversible process in a constant temperature, or work done at isothermal, work done by a reversible process in isothermal conditions. Okay. So but from all the discussion there is one equation that you must remember in mind, which is dg equals to VdP minus SdT. This is a very important relation. Okay. And we also had this equation that delta G would be equals to delta H minus T delta S. Okay. So when we have a constant temperature, then we can write delta H is equals to 0 for an ideal gas. So delta G would be equals to minus T delta S. Delta S would be equals to Q reversible by T. So this implies that delta G would be equals to minus Q, and minus Q would be equals to W, because at constant temperature delta U for an ideal gas is also 0. So this would be equals to W, which we have also seen here, that delta G would be equals to Wg reversible in isothermal conditions. Okay, so with this we come to the end of this lecture. In the next lecture, we will be seeing more on the Gibbs free energy and the work done, or rather the useful work done. Okay, and we'll also be seeing more on this very important formula. So till then, good luck and goodbye.